So, hi, welcome you all to another presentation. Today, we'll see the time response analysis of control system. By the way, today we are going to see the lecture number 23 and we are going to see about time response analysis, which is one of the topmost important topic of control system subject, and it is very important in competitive examination point of view. So you will get most of the questions, damn sure questions you will get from this time response analysis. Therefore, this is the another uh, beautiful topic we are entering today. Therefore, please, I request you all to carefully listen and follow, and you will get a lot of information in this. Actually, today in this presentation, I would going to brief you the very basic fundamental uh, fundamental information about this time response analysis of control system. So, what is time response? What is a time response? What is a response first? A response is nothing but output. For any given control system, normally till now we have seen for any system we are applying some input and the system is generating or producing the corresponding output. That output is called as a response. A response is equal to your output. Therefore, therefore, so in this time response analysis, basically, I will let us consider let us consider a closed loop control system as we have seen in our previous presentations. Just I will explain you that. Let us consider a negative feedback control system. This is what your C of S, this is what your R of S in general, and this is what your feedback element of H of S, and then this is what your output we are feeding back. Is it not? So this is what we have seen. This is give negative here, and it is always it is plus. Basically, it is minus. It is called a negative feedback control system. So here R of S is your input, whereas C of S is your output, and this particular system is called a closed loop control system with negative feedback. So for this particular control system, if you write the expression for the transfer function, okay, for this we have seen the transfer function of this particular, the transfer function. What is the transfer function? Transfer function TF is equal to, TF is equal to, it is simply C of S by R of S. Is it not? C of, it is the ratio of output to the input, C of S by R of S. And this is equal to, we know that G of S by 1 plus G of S into H of S. This is what your transfer function. This we have seen. Now, as we are discussing about the time response analysis, the time response is nothing but it is the output of the system which is to be studied, which is to be analyzed in its time domain. This is actually, so if you see this particular expression C of s by R of s is equal to G of s by 1 plus G of s into H of s. And from this, what we can write, C of s is equal to, write the expression for C of s. From here, C of s is equal to, bring this R of s to the right side. Then what it will comes? This implies your C of s is equal to, what is that? So take this R of s to the right side. Then it becomes, it is G of s by 1 plus G of s into H of s, everything just you keep in bracket, the total into R of s, is it not? Into R of s. This is what your output. This is what your output in S domain. This is in terms of S. This is what your equation number 1. This is what your equation number 2. Okay, now this is what the expression for C of s equal to this one. This is for expression for C of s, nothing but your output. This is what actually the Laplace transformation of output. All this is in terms of Laplace transformation only. R of s is Laplace transformation of your, actually your input is in general R of t in general. Is it not? In time domain, your input is nothing but R of t and your C of s is nothing but your C of t in time domain. Okay. So now all this is in terms of your Laplace transformation. Now if you take the inverse Laplace transformation, if you take the inverse Laplace transformation of the C of s, then if you take the inverse Laplace, means that that is nothing but so your output is C of s is equal to G of s by 1 plus G of s into H of s multiplied with R of s. Clear? Means that if you consider this entire part with some other, if you define this entire thing as some m of s, let us say instead of writing all these things repeatedly, let us assume that the everything, the total part G of s by 1 plus G of s into H of s equal to some m of s, then it comes m of s into R of s. This is what your C of s, is it not? For this, you apply the inverse Laplace transformation by applying inverse Laplace transform or transformation, inverse Laplace transformation, then it becomes, this implies LT inverse C of s is equal to L inverse, or sometimes you can write like this also, no problem, LT inverse of M of s into R of s. This implies, so it is C of s actually, if you take the inverse Laplace transformation, then again it comes to time domain. Initially C of t we have considered C of t, if you take the Laplace transformation to the C of t, then that C of t becomes C of s. If you take the inverse Laplace transformation to C of s, then you will become, it will become C of t. This is nothing but your C of t. This is nothing but your C of t. This implies it is C of t is equal to, this is what LT inverse of, it is M of s into R of s. This is what your C of t. This is what the this is what the output or the response in time domain is time domain. Now listen very carefully. This C of t is nothing but this much. Now this is what your C of t actually. Your C of t is nothing but this much. Now this particular part or this particular output will consist of two important parameters. Means the output of control system, the output that C of t is consist of two important parts. So we have seen that C of t is equal to LT inverse of your M of S into R of S. Basically, this is in general. So this particular part has two important parameters. Two parts it has basically. One is this is what your response. C of t is nothing but output. Output is nothing but your response. Okay, this is what your response. This is what. So in this you have two important parts. One is transient response. One is transient. One is transient response, and the second part is steady state response. Second is steady state response. Clear? Therefore, your response is nothing but the output of the control system, and that output or that response will consist of two parts, two parameters otherwise. Those are, one is transient response and second one is the steady state response. This total collectively or the combination of these two is called your time response. Is it not? So your time response is nothing but whatever the headline we have put here. This time response is consist of two important parts. One is a transient response, second is the steady state response. Therefore, in further presentations, we will see what is the transient response and what is a steady state response of a control system. Right? Now, what is a transient response? Transient is nothing but switching. Switching means from one position to another position. Switching of the state of the system, or otherwise you can say transient response is nothing but it is the response of the control system by changing the input from one state to another state, because the input will varies and the input depends on time. So time response, in time response analysis, your input depends on time, correspondingly your output will also depends on time. Is it not? Therefore, the input, whatever the input you are applying to the control system, basically that will changes, and that will changes from one state to another state. So that is called transient response. Transient response is nothing but it is the response of the control system where the input changes from one state to another state. So in that case, what is the response is called as transient response. Now, what is the steady state response? Steady state response is nothing but it is the response or it is the output of the control system at which the time t tends to infinite. As the time t tends to infinite, what is the output of the system? That is called as the steady state system. Steady state means the time is reaching to infinite. So at that situation, in that situation, what is the output of the control system is called your steady state response. Therefore, transient response is nothing but it is the response of the control system where the input changes from one state to another state. Whereas the steady state response, this is the response of the control system where the time t tends to infinite. Okay, therefore these two we have to find out this response, and again we have to find out this response, then you sum up, and then that gives the total time response of your control system. Total time response of the your control system. Therefore, this is what brief introduction about the time response analysis. And in general, in general, in control system, normally the input may not be known, may not be known. So the input normally it will changes. Sometimes the input may be a sudden shock, or it could be a sudden change in velocity, or it could be an acceleration, is it not? Therefore the input will not be known ahead of the time. That's why in this particular, under this particular headline, and as per our control system, normally we have to give some standard input signals to that control system, and we have to predict, and we have to see by applying certain known standard test signals. There are certain standard test signals, those are to be applied as input to the control system. By applying those inputs to this control system, and we will analyze and we will study, okay, the behavior of the system. Okay, that's what. So you can treat those are the standard test signals to be applied for a control system in order to study the behavior of the system. Therefore, now we will see what are the standard signals, what are the standard test signals that are to be used in control system. So the very important is standard test signals. Standard test signals to be applied as input to this control system, whatever the circuit I have drawn. So your R of S is there, no, or your R of T. So at that we have to apply. What are the standard test signals? So basically we have the the first one is step signal. The first is the step signal, and the second one is ramp signal, and the third one is parabolic signal. Parabolic signal, and the fourth one is impulse. Impulse signal, and then some sinusoidal signal. These are the basic signals that are to be considered as standard test signals and are to be applied as input to the control system. Okay, these are the basic signals: step signal, ramp signal, parabolic signal, impulse signal, and then sinusoidal signal. Out of all these things, the very important and the very basic signal is your step signal, because it is very easy to generate and it is very easy to analyze of the characteristic of a system. Therefore, this is the very basic reference signal. Step signal is the very basic standard signal that is to be analyzed very easily, right? So then we will see what are the definitions of this signal, basically how these signals are defined. There are some mathematical expressions are there in step signal. Okay, signal is nothing but all these signals are to be applied as input only. Always remember that. So these are to be used as input to the control system in order to study the characteristic of that system. Is it not? So the first signal is the step signal. So what is a step signal? Is there any mathematical expression for that? How a step signal can be defined or can be represented, we will see. So the first one is the step signal. What is a step signal? Step signal is nothing but a step is a signal. A step is a signal which is available for t is greater than or equal to 0, and for t is less than 0, the value of step is 0. Is it not? Step signal is nothing but it is a signal which is available which is available for t is greater than or equal to 0 and for t is less than 0 the value of signal is 0. Then mathematically a step signal can be represented as, okay, step signal can be represented as r of t is equal to, because why r of t I am taking, no, because in our control system your input, what we are how we are representing our input, r of t only, that's why here I am considering as r of t. Okay, r of t is equal to, it is 1 for t is greater than or equal to 0 and it is 0 for t is less than 0. This is the definition of your step signal, remember. R of t is equal to 1 means, so graphically it is represented as like this. Take x-axis. In x-axis you can consider as time, actually it is time, and on y-axis you can show your input r of t. So it is t, it is time x-axis, and on this x-axis we will represent the time. It is initially 0 actually. So as per this definition, for t is greater than or equal to 0, your r of t equal to 1 means the magnitude is 1 here. Okay, t equal to greater than or equal to 0 means starts from 0, you can take any value up to 1, 2, 3 and so on and so forth. You can go up to plus infinite, no problem, you can go up to so on and so forth. If any magnitude you take on the x-axis, that is on time axis, you can say the value remains 1 only. And for t is less than 0 means left side of 0. So here in left side part, this is what t is less than 0. This is the t is less than 0 part, means left side of the 0. This is what from here, this is the limit, t greater than equal to 0, nothing but this portion from 0 to right side basically. So here, so at 0 the magnitude is 1, 1 it is 1, 2 it is 1, means you can represent like this, it is a constant like this. This is what your step signal, the magnitude is 1 means t equal to, t is greater than or equal to 0 is nothing but this area, this. So from 0 to plus infinite you can go up to, so for this range of this time your magnitude becomes 1, whereas for other that is less than 0 the value is 0, so it means it is 0 actually. Here no signal, no magnitude, nothing, it is 0 here. So this is what your step signal. This is what the step signal. And now one more important thing is, as we are considering the Laplace transformation of each signal, then what could be the Laplace transformation of this r of t? R of t. So as I have explained you in our in the very beginning presentation, the input and output normally we will consider in terms of the Laplace transformation. So what will be the Laplace transformation of your step signal r of t? Means, let us say in general, I will give you the definition. Let us say the definition of Laplace transformation. Laplace transformation. What is a Laplace transformation? Simply it is represented by L of t. Laplace transformation for any signal means, say for example, if any signal f of t is given, f of t is a given signal or given function, you can say, no problem, and it is defined over a limit 0 to plus infinite, or sometimes it could also be minus infinite to plus infinite, no problem, no problem. So f of t is any given function and it is defined over a limit 0 to plus infinite or otherwise minus infinite to plus infinite. Then the Laplace transformation of f of t, Laplace transformation of f of t is given as your capital F of s, capital F of s, and this is equal to, this is equal to, what is L of f of t? There is a mathematical expression that is nothing but, so I will I will explain you here, you will understand, because it is very basic definition what I want to explain you that. Laplace transformation of f of t is equal to nothing but your f of s. This is equal to, there is a mathematical expression for that, that is nothing but either you can take 0 to plus infinite or otherwise minus infinity to plus infinite, then it comes something like this, e power minus s into t into f of t dt. Remember, this is the definition of a Laplace transformation of function f of t for any given function f of t, and which is defined uh, over a range 0 to infinite, or you can take minus infinite to plus infinite, no problem. Again, in Laplace transformation, basically there are two types depending on the limits. Basically, this is called unidirectional. This is called unidirectional Laplace transformation. Unidirection, because that basically this concept we will be come across in your mathematical subject basically. Okay, unidirectional or one directional Laplace transformation or unidirectional Laplace transformation. Uni means one. Okay, that is especially 0 to plus infinite, means from the right side of your time limit. Whereas if you take minus infinity to plus infinity, then it is called a bidirectional Laplace transformation. So normally for our understanding, you can take unidirectional, you can take 0 to plus infinity only. Okay, so if you consider this, so it is 0 to infinity e power minus st f of t dt. This is the standard definition of a Laplace transformation of any function. Is it not? Now here our f of t is nothing but this. Our f of t is nothing but r of t. What is our actual function? What is our actual step function? It is r of t. R of t is equal to what? R of t is equal to 1 for t is greater than or equal to 0, and it is 0 for t is less than 0. Clear? This is what your r of t basically. So this is what your step signal, and it is defined as 1 for t is greater than or equal to 0. This means t is greater than or equal to 0, nothing but your t value starts from 0. Up it goes up to, you can take plus infinite, no problem. You can take, this is your starting limit, and where it is ending, we don't know. It is going up to plus infinite. Therefore, if you substitute r of nothing but your f of t is nothing but r of t here. Okay, your f of t is nothing but r of t. Substitute our step signal information in the standard definition of Laplace transformation. Substitute our r of t here in the standard definition. Then how it could be? This implies L of t. Then your f of t is nothing but r of t. Is it not? So small f, after application of the Laplace transformation, small f of t becomes capital F of s. Similarly, here small r of t can be converted into capital R S. This already we are know this. R of s is equal to, now limit, it is 0 to infinity only, because t is greater than or equal to 0 is nothing but 0 to infinity we have to take. Starting limit is 0 going up to plus infinity. Is it not? E power minus s into t. What is your f of t? F of t is nothing but your r of t. F of t nothing but your r of t into dt. Is it not? Now our input signal, the information about our step signal, I have substituted in the standard expression of our Laplace transformation. Now this is what my expression. Now simplify this. You simplify this, what you will get? You simplify that. I will solve for you. So if you simplify this, then this implies your r of s. Directly I will write r of s. Okay, that is equal to, now see here, it is 0 to plus infinity e power minus s into t. What is your r of t? R of t value, what is r of t? I mean, in the 0 to infinity, what is r of t value? R of t value is 1 into dt. Clear? R of t value is 1 for t is greater than or equal to 0, nothing but 0 to infinite. Basically, the meaning of the limit of that t value is 0 to infinity. This implies 0 to infinity e power minus st into 1 into dt, nothing but it is 0 to infinite. Multiply e power minus st into 1, you will have e power minus s into t only, and then dt. Clear? Further, now integrate e power minus st. If you integrate e power, okay, the standard definition is, for any standard, integral of e power, say for example a into x, for example, into dx is equal to e power ax by a. Remember, integral of e power ax into dx is equal to e power ax by a will come. If it minus comes, no, then you take minus here. So similarly, here what we will have, e power a t, let's say for example, then e power minus s into t will be there, minus s comes in denominator. Clear? Your minus sign is there, no? Your a is nothing but s actually. So a nothing but your s. Minus sign is there, therefore minus sign you have to write here. Then in this you substitute 0 to plus infinity. You substitute limits there. Then this implies what is that? So minus 1 by s you can take as common. You take minus 1 by s outside. Then e power minus s into t. It is 0 to infinity. This implies further minus 1 by s. Okay, in place of t, substitute the upper limit minus lower limit. Is it not? This is the upper limit, this is the minus limit. Always the upper limit is to be applied first, minus lower limit is to be applied then. Then this means that e power minus s into what is upper, in place of t you have to substitute. Therefore, e power minus s will be there. In place of t, substitute plus infinity. That is minus lower limit then. E power minus s, lower limit is 0. This implies minus 1 by s. Okay, then if you see minus s into infinity, e power minus s into infinity, s into infinity is infinity, e power minus infinity, e power minus infinity is 0. The value of e power minus infinity is 0. Minus s into 0, 0 multiplied by something 0, the total is 0, e power 0. This implies it is 1 by s. It is 0. E power 0 value is 1. Therefore, minus 1. It is minus into minus plus. It is 1 by s. This is what your answer. Therefore, r of s is equal to 1 by s. And finally, you can write that. R of s. Finally, you can write that r of s is equal to 1 by s. This is what? The Laplace transformation of your step input signal. So if you apply the Laplace transformation to the step input signal, the Laplace transformation of step input is equal to 1 by s. Clear? While solving in the problem in the subsequent presentation, it will be more helpful. That's why I am explaining all this. So with this, just I want to finish this presentation and let we continue in the subsequent presentation. I hope that you enjoyed this and be prompt and continue to follow the lectures which I am going to presenting before you all that. So in the sequence, if you follow, then definitely will get the very meaningful understanding of the subject concepts. Okay, so with this I would like to close and we will continue in the next presentation. Thank you one and all.